Oh, wow. You're good.
Wow. It's scary when you have a room. Half the people know the topic better than you do. So just to kick it off, I'm Jim Miller. I'm one of the PMs on the Com+ Runtime. This is the first in 2 officially scheduled short courses on the Com+ Runtime technology. This week, I'm going to concentrate on what we call the VOS level, the Virtual Object System. That's sort of where I spend my time. And that's the type system, metadata, the intermediate language, the compilers for the intermediate language, the JIT compilers, so forth. Next week, we're going to do what I like to call the enterprise story. And that'll be things like garbage collection, especially the large-scale garbage collection issues, assemblies, which is sort of the deployment story, contexts, and remoting. So it's sort of a 2-part thing. If this turns out to be useful on either side of the house, or hopefully both, we'd like to consider a couple other ones. The 2 that I've heard about, and I'll come back at the end and ask if other people have other suggestions. One is the whole security story, which is worth at least an hour on its own. And somebody suggested that the last one, which I kind of like, because it's the one where I get to sit in the audience and you guys get to come up and tell us what's wrong. We really would like to have that dialogue, and there are lots of ways to have dialogues like that in the company. We like to try the one where we actually get together and talk face-to-face instead of trying to send it up management chains and down management chains, and that's been inconvenient for both sides for a long time. So the agenda for today, as I said, is really the sort of the 4 pieces. It's actually a 5th. I'm going to give you a brief architecture overview. For those of you who saw the original invitation, the hope was that everybody here went to or has the equivalent information of what I gave in the overview talk about 2 weeks ago. So the goal is for me to dive down farther and be more technical. In doing any kind of course like this, you have to decide whether you're going for breadth or depth, and I chose breadth. So otherwise we would have had, instead of 2 courses, we would have had to have a good 15. So I'm willing to dive down.
Are these slides online?
They are online. I will send the URL out. They aren't in a convenient place yet. And I guess we ran out of handouts, so I'm sorry about that. So the overview, really, this is sort of the block diagram of, if you like, of the entire system. So today we're going to actually be talking mostly about the stuff down here on the bottom. Managed objects, for those of you who like the other way of speaking, that's garbage collection. Metadata, which is the descriptions of those objects. A type system. 3 different kinds of jitters and a native compiler. And then the whole thing is wrapped up in what we call the execution engine. And then layered on top of that, languages which target it. And on top of that, our base class library, reflection classes, the security, the deployment story. This is really where next week is going to concentrate, and we sort of are somehow skipping this layer. As far as the sort of the picture of how this works from a usage point of view, you pick your favorite programming language, which might be a standard language, it might be a scripting engine, whatever. That's compiled down typically to our intermediate language, which is what I'll spend about a quarter of the time on today. And from that, it can go straight into the runtime and be, actually we now call it client-side compilation. I think that's sort of a better term than jitting for a variety of reasons, to produce native code. Or you can go through an optimizing compiler and get something out that we call opdil, which I'll also talk about, and that goes in and actually gets compiled by this particular compiler. Or you can go out to an optimizing compiler, get native code for your platform, and we can run that directly. So that's sort of your fairly standard thing. In some cases, there's a linker step that occurs in there for VC in particular. Yes? Yeah, I'm not sure. Yeah. What do you know? The mouse will appear when you touch it. Okay, good. Thanks. So that's sort of the general overview of the system. Now I want to spend time on the type system, which is sort of the unifying principle that runs pretty much through the whole of the COM+ runtime architecture. I'm giving you the URLs for the detailed specs here, and of course in the handouts, as I say, I will put them up. Our website is COM Runtime, and then most of the stuff lives under specs. And I believe that the slides themselves will go COM Runtime. There's another subdirectory called Presentations, and it'll wind up there. So what have we got in our type system? Sort of the high-level view there, the two big notions are there are types and there are locations in the machine, and there's some relations between those. Types, at least some of the types, have members, so there's substructure inside of there. There's a whole series of naming issues. We have a way of thinking about the type system that I kind of like, which is contracts and signatures, where the notion of signature means the machine enforceable part of the contract. The contract encompasses more than that. Type definers, things that define new types. And then inheritance, implementations, and the relationship with the contractual obligations, which is really what drives the system. So the sort of the details on types and locations. We have two kinds of types. Value types, which are really user-defined types like complex numbers or nullable integers that should be thought of as sequences of bits. And they should be thought of as there is no object identity. Yes?
Sorry, what is a nullable integer?
SQL has nullable integers. It means it's either not an integer, or there's nothing there, or it's an integer. So it's sort of an integer plus a bit. And they're kind of inconvenient things to do in programming languages because they don't fit in one word. So a typical thing to do would make a value class where you say the flag saying whether it exists, and if it exists, what its value is. Variants are another one, another user-defined type. Typically, for good uses of value types, if you will, they're small. You don't make really big things because, in fact, you usually pass by value. There's an equality operator on value types for one particular value type. You can tell whether it's equal to an instance of the same one, user-defined. But there's no identity operation. So the system is free to make copies as it will. We never use the location in memory or any other thing to tell whether two value classes are the same. It's the same idea as an integer. You don't typically ask, is the integer living in the same place? It's not a sensible question. So that's what a value type is. But we have the operation, it's a traditional operation from the old days of the Lisp community and elsewhere, of boxing, where you take the value type, you convert it into a real honest-to-goodness object, and then it can inherit, and it has object identity and so on and so forth, and you can go back the other way. So if you keep it boxed, you get identity. If you unbox it, you get passed by value and sort of get your choice. We also have reference types. These are your typical objects in an object-oriented system. They're self-describing at runtime. We have several types of reference types. So the first type of reference type is an object. The distinguishing feature of an object is it's self-describing at runtime, and it has inheritance features. So you can actually walk up to the actual representation in the machine of the object, and you can ask it, what class do you belong to? What's your superclass? What's the members of your fields? How many fields do you have? What methods do you? All that kind of stuff. That's the self-describing property. Yes? There is marshalling support for value types. They're marshaled by value. That's one of the reasons they're nice to have. That's all of next week's discussion about remoting and the enterprise, but the fact of the matter is there's static information that's stored, and we'll talk about the metadata. The metadata is available while it's not on the instance at runtime, it's available at runtime, and that drives the marshalling. So it's sort of static information, but it's not in the representation, but it's in the code path, if you will. You know what the type was. So please do feel free to ask questions. That's a large part of why we're doing this, is to hear questions and have some people in the audience who are going to. Yeah, go ahead.
Is it describing on the actual physical machine, or would you optimize it as an extra bit away?
Right now, it's self-describing on the actual machine, optimizing. One always optimizes, and one optimizes throughout. So I don't believe we have any plans to optimize anything right now on that. Yeah.
There was some discussion of having a third session on this specifically to gather feedback from MSR.
Yeah, I covered that.
Do you know what so that is going to happen?
It will happen if these things are successful and people want it. Then we will do that. There's no question about it.
And successful means a lot of people show up and ask really tough questions, right?
and they show up the next time. Yeah, right. Yes. Okay, so interface, and as I said, we want to do it sort of in that. If we decide to do that one, it's sort of an inverse one where we'll have some COM+ runtime people sitting there, and we'll hear what you've got to say and have a dialogue about it, as opposed to. Well, never mind. Right. So that's objects, first reference type. Second reference type are interface types. Now they're different in that they are partial descriptions. They're descriptions of behaviors, and they're usually implemented by many object types. So they're reusable quantities in terms of description of what you would like the behavior to be. You create an instance only of an object, but that object might implement many different interfaces. So you get interfaces because of the type that you've chosen, the object that you've chosen to create.
Can you give an example?
Oh, COM. Any interface you can think of. I mean, collection interface, something that has ordering. Ordered is an interface. It means I have less than and greater than operations. Anything like that. So it's basically a set of operations that are supported with a well-understood semantics, which we call the contract. And so that's what an interface is. And then I make a particular implementation, and I say, that has that interface. Therefore, you can get at all of those methods that I promised you were there. So that's the idea. Pointer types are the third reference type, and there's some debate about whether they really belong in this category, but I kind of like them here. They are just what you think. They're machine addresses. There's possibly some static information about it. So you might know that this is a pointer to an integer. But you can't really look at either the pointer or the thing it points to and say, was that a pointer to an integer? There's no way to actually do that. But it's available because you know that from the flow of control, for example, that it had to be a pointer to an integer. So there's no runtime description for them. Okay, so those are the three fundamental reference types in the system. Yeah?
Interface types, are those composable? Can you derive, composable in the hierarchy? Like two-type hierarchy?
Yes. You can sort of depends on exactly what you mean.
Right.
You can have one interface that implements another interface, and yeah, it derives that way. And a single class can implement many interfaces. So it's multiple inheritance, if you like, on the interface side only, single inheritance on the class hierarchy side. I'm not sure that's really answering your question. Right.
Should I think of this being like Java interfaces?
Should you think of it as being like COM?
Should you think of it that way? You shouldn't think of it that way. However, it might be a fact. I don't know what else to say. Right. Actually, before I go any further, I actually do need to say this. The content of this talk is considered very confidential to Microsoft, and I should have in fact asked. I assume that everyone here is a full-time employee, and that it is in fact not to be spread out farther than the invitation list for this meeting. So within research is fine, within the particular organization that this was disseminated to is fine, but it is not intended for general dissemination, either within the company and most certainly not for outside the company under any circumstances. So, thank you, marketers, proceed, and lawyers. Okay, so that's the type side of the equation. And then there's the locations, places in memory. So our version of this is that locations hold values, which can be instances of value types, or they can be instances of reference types. And they have a static signature. So for each location, we actually know what type of thing it holds and some flags. And I will go into the details of what the signatures are in a minute. So the locations have signatures which are enforceable pieces of contract with them. Yeah?
How do you do that with small things like bytes and get acceptable
I'm sorry.
How do you do this with small things like bytes and get an acceptable overhead?
Oh, I mean, it's static descriptions of what's in the location. It's not, we're not carrying around at runtime. It's just, basically, like, variables have types. So that tells you all that's what I mean by that. So what goes into a type? Well, typically fields and methods, those are the sort of two things we put in our types. And then there's these, what I call mostly orthogonal attributes. It's not true, quite, that you could have any conceivable combination of the things here. If you count it up, that comes to like 800 different ways of combining things. And most of them make sense, a few of them don't. And the details of that are still being hashed out and argued because they differ from programming language to programming language. So we want to pick a set that seems reasonable at the lower level for lots of programming languages to use, but the details aren't settled. But it basically boils down to this. Things are either static, meaning there's one of them independent of how many instances of the type you have. Things that belong to an instance, which means that it's shared by all the objects, or virtual, meaning that it's shared by the objects but can be overridden in a subclass. So that's your typical Java, VC, Smalltalk distinction there. The parent or the child could be one or the other. So the parent could be a virtual method and the child might not, or vice versa. And some of those combinations are legal, some aren't. There's a notion of private, public, and restricted access. So that's visibility to things that are not part of this class or this class hierarchy. And we fully support private and public, and there's an argument about exactly what restricted means because each programming language has chosen its own meaning for that, and we have not fully decided exactly what we'll be supporting in that regard. Final versus not final. You can't have a final parent and a child, so it doesn't make sense in that case. But final means that you can't have children, effectively, in a class hierarchy sense. Value types, interfaces, classes, that's what I talked about before. Within them, fields and methods. And then finally, for visibility essentially outside of your compilation unit, there's a question of whether, if you've defined something, is it visible only in the compilation unit? Is it visible to everything that's been linked together by the linker into what we call a module? Is it visible to everybody who is in the same deployment unit, which we call an assembly, or is it visible outside of the assembly as well? So you get all of those combinations on all the pieces. Yes, sir?
What does global mean?
Global means that it is accessible to things outside your own assembly. So another assembly might...
But there must be some other bound of visibility.
No, this would be
the same process of virtual machine universe.
Universe. This means basically that you could go out to some. You are willing to have your type registered in a universal naming scheme that anybody on any machine in the world could get you and presumably find you, download you, and make instances of you. So that's what we mean.
So there's a name collision problem.
Yes, that's what assemblies are about. Assemblies are about part of that problem, and the question is, what do the assemblies do to get to the universal namespaces, and that's all next week. Yes?
Is an assembly, does it have a single address space associated with it? Can it have multiple?
Assemblies really are a major piece of next week's talk. I'm going to give one slide on them today. I don't want to go on the whole today. And I will also say, just up front, the assembly story isn't anywhere near finalized yet. So there's going to be lots of open issues, and in fact, we want to explore them. Yes?
So just jumping back to assembly module, is that just what we typically think of as a COM object in DLL?
DLL is a real good analogy. It's the things that you link together from the linker, and you get one unit out that you can load and use. Assemblies can have many of those together along with other resources that they consume. So think of an assembly, one kind of assembly, the whole application, and then you get a sub-assembly too. Other questions?
I just want to make a point. I've raised this question with the institution team. We've been using Rivet assembly for a long time to make something different. So I'm hoping the result doesn't know what you guys giving up on it.
No comment.
Just letting you know.
That's right.
You have to publish first.
Name conflicts are like the worst things in programs and in the real world, near as I can tell. Next major topic is this notion of contracts and signatures. Contracts are generally, from my point of view, mostly unexpressed, unfortunately, but they are the guarantees that are being made by some unit about how it will perform and how it's to be used. There's an enforceable part of that we're able to mechanically check and verify that it hasn't been violated, and we capture that in something called a signature. There are other things that we don't know how to capture, like the meaning of what happened. I mean, you could go to denotational semantics and try to do stuff to capture these, but typically we don't in programming languages. A signature, for example, would be a signature for a method would be the types of its parameters, the type of its return value, and a little bit more information. That doesn't actually tell you what it's computing. So what it's computing is part of its contract, but its signature is the part that I mechanically know how to verify. And over time, that what's mechanically verifiable might grow, and signature might not be the right word for it, but today signature is pretty close to what we can capture. So the kinds of contracts we have are class contracts, which consist of methods, fields, properties, and events. Interface contracts, which have methods, static fields, properties, and events, but not classes. And then methods, properties, and events themselves. And for each of those, you want to be able to say, for this class, it has these methods inside it, it's used for this purpose, it must have the following things in the environment. All of that would be the contract. The enforceable part of that, in this case, would just be the list of methods. The signatures, when you go down to what's the enforceable part of the contract, well, on every value, there's the notion of whether it's constant or not. And I don't want to spend a lot of time on these. It's the most bizarre one, and it's somewhat contentious within our own group. But it's basically the one that says you can't change this value. It's immutable. It's not part of its type, it's part of the value. So the type might have mutation operations, but I won't be mutating this one. And you can say that in a certain way in language like C++ with the const attribute. Const actually means two things in C++. This is one of the two. It's the one that says you can't change its value at runtime. On locations, we supply everything you have on that was a typo I didn't catch. That should have said values. So you get the constant idea. But you also get read-only and volatile. Read-only says you can't change this location. But if something is read-only but not constant, you can't change the pointer, but you can indirect the pointer and change the object. That's the idea. And volatile means this location is volatile. You can't rely on it being the same the next time you go read it. So if the user has said read it twice, you can't cache in between because it might have changed. And if the user said store it in twice, you can't suppress the first store because somebody else might be reading it in the interim. On parameters, you get the same thing you said about a location, because they are locations, but you also get to add two things. Whether it's passed by reference, as opposed to by value, or whether it's what we call a typed reference, which is it's what you need in languages like VB, where what you want to pass from the caller to the callee is an address in memory and the type of that address. So you, in fact, at runtime pass, guess what? Two things. The address and something that tells you what the type of that address is. And then, of course, the receiver is intended to do type checking on that, and we do that in a type-safe manner. The only operations that can manipulate those places check the types before extracting or storing into them. And then finally, on a method, you pass the parameters, and you also have the ability to say that it's got a variable number of arguments, in which case we have a type-safe mechanism for passing as many or as few arguments as you like from the caller to the callee. Is that pretty clear what we got on contracts and signatures? type definer is sort of a loose term. Some kinds of classes are created automatically by the COM+ runtime based on the description that's been provided. So if you're writing a compiler and you want an array of integers, you don't have to create an array class, which is a fairly complicated beast. You simply say, I need an array, its element type is integer, it has this many dimensions, and we manufacture the class on the fly. So arrays are one kind of type definer. And the description that you have to supply is the type of element that's allowed in the array, the rank, that is the number of dimensions, the lower bounds, or the lower and upper bounds. You can supply all or some of these in various combinations, and we'll manufacture classes that correspond to that. When we manufacture the class, it also automatically gets things like the length, which is the total number of elements, a get element, a set element, and there's a bunch of other stuff on arrays. So that's what we manufacture for you automatically. And we do the same trick for pointers. You give us a description of the type that it points to, and we manufacture all the information we need to deal with it, and including for functions. Not true today, but we will soon be able to also manufacture. You give us the signature, and you'll get a type-safe function pointer.
What's the purpose of this? What problem is being solved by having this?
The problem that's being solved is a combination of the complexity of the tool that's needed to generate things for common cases. So it's inconvenient if all your tools have to synthesize a very similar data structure, namely an array, when they could just give you a simple one saying what kind of array they want.
So, but then I'm confused. Are you building the classes or the instances of the classes?
Well, both, but this I meant the type description itself.
Okay.
You give us a minimal description of it.
Which tools need this?
Oh, a compiler, for example, like C++, has the notion of just saying int bracket bracket, and rather manufacturing all the methods that we say are on a class so that everybody can on an array that everybody could interoperate with. They just tell us, I want an array of integers, and we manufacture all the gunk. Otherwise, they would have to produce a lengthy description.
Manufacturing the gunk that is the automatic part.
Correct.
Okay, cool.
Right. They all look the same except for a little bit of stuff, and we do the work of manufacturing the standard piece of it.
Wouldn't a good macro system solve that?
Macro doesn't make the file size that's transferred across with the metadata any smaller. I mean, it could if you did those kind of macros. We don't have that in our metadata format, so it serves that purpose instead. It also means that we are free to optimize those in any way we want. So while you might have to manufacture a big lengthy thing that we then take and only actually use a subset of it, this allows us to manufacture the subset we need and incrementally grow the rest of it. Whereas for user-defined things, we wouldn't know what to manufacture on the fly. These we do, and so we can special case them. We actually get a certain amount of efficiency from those kinds of implementation tricks.
Are there only a fixed number you need to?
Fixed number of?
Type definers.
Right. Currently, we only have a few of them. One of the things that's actually interesting is whether there's a way to extend that notion. And we are not, in the first release of this product, being able to address that question at all. But it's a really interesting long-term question. In fact, I won't go there. Inheritance, implementation, contractual obligations. This is sort of tying together the object-oriented world with this notion of contractual obligations. So, first rule, value types don't inherit. And that just makes a whole raft of things simpler. You can box them and get the inheritance properties, but if you keep them unboxed, they're just flat. They inherit from object, that's it. You can't add nothing to them. They can't descend from other things. Turns out to make an awful lot of stuff a lot easier. You can think of value types as C structs, but in a managed context. So what does inheriting mean? Well, our belief is that what inheriting means is that if you inherit from somebody, you promise to implement the parent's contract as well as any of your own contracts. So that is the interchangeability notion. Yes?
Do you have a notion of the contract that a class implements for its subclasses?
Distinct from... Not really, although you could argue that the distinction between public and private members is a statement to that effect. We have not thought of it that way.
Well, I mean, virtual says you can override this. Is that a contractual statement? Because a child can say,
Yes.
can finalize that and say, well, now it's not available anymore, which means they don't have the same contract as my parents.
That's a very good question. I have to go back and think about that. Somebody from our team writing that down. That's a very good question. So we need to formalize the contract a little bit more than we have. Implementing an interface or a property or an event implies fulfilling that contract as well. So inheriting as well as implementing are statements about the contract. So you basically agree to do the, yeah.
When you say property or event, what do you mean by that?
Yeah, I was sort of, I was hoping I could slip that one by. There's been some contention about that. Properties, the way I think about properties is they are, at least as we're currently handling them, they're an ability in the source language to be able to say, I'm going to reference this thing as though it were a field of an object or an array. But in point of fact, it's a set of commonly named methods and backing store information. And it's a language convenience feature that the scripting languages, for example, really found convenient. It also has very good properties for remoting because it's easy to use, but it slips in a method in the background and we can intercept the method and remote across it. So that's what a property is. An event is a similar idea, but event, the notion, with a property, the automatically assumed operations are get my value, set my value, what's my default value, change my default value, things like that. For events, the default set of operations are subscribe to the event, fire the event. I think that's unsubscribe. Thank you. All right.
So that applies to the event model too.
Yes, and right. If it is not currently planned to be part of next week's talk, but that's where it logically belongs. If we want to have a conversation about it, we are doing a lot of stuff there. Yes.
You're talking about implementing contracts and fulfilling contracts. Are those two very different things?
No.
Well, implement is like the language keyword that is
Right.
a promise. And fulfilling is writing the code that says keeping the promise.
I think I'm using a little bit of liberal English here. I was not intending to make any distinction there. Yeah.
You distinguish implementing an interface property or event. Normally you think, so the properties and events are some orthogonal thing carried in a different way. That is, the interface only talks about the method. You think you would want it to also describe the property or event behavior of the object.
We do describe them as well, but we don't. They are neither methods nor fields. They are another kind of thing, and they are described in a separate kind of way. And they map the way we are doing them right now. It is the tool's job to map those into methods and fields. So we carry the information from tool to tool. I'll get back to this in a minute. But the tool is responsible for doing the mapping. Once it hits the runtime, that mapping has to have occurred. We do not, in fact, understand what a property means other than there's some methods.
Lower-level methods that get constant in the interface.
Yeah, and we just lost. There's been some debate about this.
Delaying the binding of the stuff?
Well, it was the original purpose. Well, I don't want to speak to what the original purpose was. At the current time, it does not delay the binding. At the current time, it is simply properties and events are only for tool-to-tool communication, so that if I'm writing in VB and say I have a property, then somebody in VC who wants to use it will know it's a property, will make it look like a property in their language, whatever property means. At the runtime, it's been compiled away. It's gone. Enums are in the same category right now.
So these are essentially intentional.
Yes, thank you. That's a good way of distinguishing. These are for the intent. These are the intentional stuff. It gets compiled down to extensional properties, methods, and fields. Thank you. That was crisp. Single inheritance only. I think I talked about this. You can have multiple interfaces, but you can only have one parent in the class hierarchy. And then the weird, maybe weird, but it's the way we've been talking about it. An object can implement many contracts, And since, from my point of view, very much the contracts you implement are your type, that means an object, in my point of view, has many types. So it has the type of each of its interfaces, it has the type of each of its parents. That is, it can be used completely interchangeably for all of those. Okay, so that's the type system. Metadata. So the basic idea of metadata is that it persists the virtual object system types. It persists both references to things and definitions of things, and they're slightly separate. It's used in two kinds of contexts. It's used in the context of tools, that is, things like compilers, debuggers, and so forth, passing information to the runtime implementation. And in particular, the main impact there is we use this metadata very heavily in our class loader, in our security system, and for mapping from the type definition where we say that there must be a method named George down to the actual location where George, the implementation of George, can be found. So that's from the pure runtime point of view, this is why we got the metadata. But why aren't properties here? Well, because in fact, the runtime doesn't care about the property. It just cares about the methods and fields to which it got mapped. The other tools care about the fact that it was a property and that they might let their users see it as a property, even though the runtime doesn't understand that.
So why aren't properties metadata?
I'm sorry. I didn't mean to say they are. Properties are in the metadata. Properties are carried in the metadata. They are carried in a way that is distinct from the way we carry methods. I mean, they're different things, right?
So instead of talking about, so and events are the same way that both of those are really metadata. They're not types at all.
That's correct. Yes. Properties and events are pieces of the metadata. They are not types themselves. That's correct. They do have contracts. I mean, in that sense, they're types. They are promises that you will do something. If you say you implement a property, then there are things you must do. And if you say you implement events, there are things you must do. And there's also tool-to-tool communication. That's where I put the properties and events, because this compiler needs to know that it's a property that was created by that.
Are these properties and events definable by tool writers? That is, do you define a set of properties and events?
No.
Or
we have a mechanism for people to specify what properties they want and what events they want. We don't have a way of specifying that we want a new thing like a property. If you think about it, right? You see what I mean? It's at what level you do this, but yeah. And in fact, some tools expose VC and the late lamented VJ supplies syntax for specifying for the users to say, I wish to have this property. VB supplies one that says, I wish to use this property, and I don't know whether they supply the one that says, I wish to create a property. So those are independent things. For tool-to-tool communication, there are, I only put two down here. There are actually three uses of the metadata between tools. One is what's called the CLS, and there's some debate about what the expansion of those initials is, so let's just call it the CLS, shall we? Is about interoperability. There's a set of language features that is being discussed, and we're sort of coordinating that discussion, that our major languages have agreed to implement, and we're going to try to get other languages to buy into and interoperate across that spectrum. And that includes properties and events and classes and interfaces and enumerations and a lot of other things. And that's what the tools communicate to one another. A particular tool like VC or C++, ISO standard C++, has a bunch of things that it knows about and its programmers use that VB programmers are not likely to ever care about. Volatile is actually one of those. Unaligned accesses is another of those. So the metadata is built such that a particular tool can also put its own private information that it wants to transfer within itself, so that we just use the metadata as a way, since the metadata actually goes in object files and exe files and DLLs. It's a convenient way of transferring stuff. You don't get this business of, I've got a DLL here and I've got a typelib here and they're different and I don't know if they're in sync or not. You just put the typelib inside the DLL, they don't get out of sync. They get out of sync with some other DLL, but they don't get out of sync themselves. And so the metadata is actually a convenient mechanism for that purpose. Like it says in big letters up there at the top, details next week. That's another way of saying I'm not ready to be grilled on this yet. So what is an assembly? And with apologies to Tony who owns Assembly TM, this is Assembly Com Plus. I don't know what it means. It's actually not us. Anyway, who knows? We call them assemblies. They're the unit of deployment. They are the thing that you say, I want one of them guys on my machine. Some people like to say that's a logical DLL. I actually find that not a way I like to think, but there it is. In our world, assemblies have manifests, that is, table of contents basically, that are used for resolving all cross-assembly references. So if your component is inside an assembly, you can talk about things inside that assembly freely. If it wants to talk something outside, it has to go through the assembly to have resolution happen. And it's the assembly that really plugs it into some global infrastructure for finding things. So if you're not deployed together, then you need a way of going out to the outside world. And we just basically said that is what an assembly is, and the manifest is the thing that is doing that mapping. Using manifest makes the assembly self-describing and self-registering. So if you bring an assembly down, bringing it on the machine registers it. That registering is not to say we scribble all over the registry TM, right? We do some other thing which self-registers it. Manifests also specify the policy, since they're in charge of resolving things outside of themselves, they are the thing that decides what the policy is for going to an external thing and saying, for example, I require exactly the same DLL I was compiled against. I won't take a more recent version. Or saying, happy to have a more recent version. Or say, any version after this. Or whatever. All that policy is in that manifest.
So that allows you to version sort of the modules inside the assembly. Is there a mechanism you have for versioning the assembly itself? Once you bring down a manifest, is that going to be the manifest on your machine forever, and it sort of mutates into new things, or can you download a new version of that?
You could download a new version of the same assembly in some sense. You get a new manifest, and other assemblies that are trying to find the assembly would have to pick which version they wanted. So I'm not quite sure how to answer the question. You get the whole assembly, and from one assembly you refer to another assembly, and there's versioning control at that point. That's the best I can answer.
So the manifest is really the mechanism that's responsible to sort of handle
how can I put that? I mean, the manifest is, it's the data file that goes into the mechanism. So having the sheet of paper without the mechanism doesn't help you, but yeah, the two are kind of equivalent in that sense. Yeah.
How do you name the
That's next week's discussion. Right. And I think that's actually quite contentious, and it's the core of the actual issue. I mean, at some point you get a naming issue, right? There's the naming issue. We managed to move the naming issue to one place, right? Which is better than it used to be, because it used to be all over the place. So what are we actually cramming the metadata? You can define a type, a method, a field, a property, or an event. So those things you can express the definition of. You can persist references to types, methods, and fields. But remember, we said the runtime system doesn't have a notion of properties and events, and so it can't support the notion of referencing them. I mean, maybe it could someday, but it doesn't today. So it has definitions of all of those things, references to most of them. We have a naming hierarchy in the sense we just talked about. Assemblies are used to locate modules or other assemblies. They locate external assemblies and they locate modules within themselves. Modules hold named classes, named interfaces, named properties, named events. Classes provide names for methods and fields, and methods have named parameters. So, it's sort of trickle-down hierarchy. Yes?
Is that name parameters in the sense of the and borrow? Or is that just the conventional language?
That's the conventional. I just meant the conventional as in C. Oh, not by name. That's no. Yeah. Yes, thank you. Right. Good grief, no. Okay. Metadata also has the signatures, the enforceable part of the contract. That's how we get the contract that needs to be enforced. It also maps from the method definition down to its implementation. That is, say, it says, you said I've got this type with this method on it. It's at this address in this module, and that's been loaded into memory here. And then it can also hold custom data of the tool's choosing. Yeah.
It's possible to enumerate the different classes in a particular assembly or particular
I think I get to that in the next slide. Yeah. If I don't, ask me again before I get out of metadata. Okay. Signatures and bindings. So signatures, again, the enforceable part of the contract, and the enforcement mechanism is the binding. The binding is the thing that says I've got a reference, I've got a definition, do they match, link them up. So the metadata engine itself, which is part of the COM+ runtime, converts refs into defs if they're within a single module. And that's done either at compile time for some tools, and it's done as part of the linker for other tools. And so its job is basically to convert all the internal references, if you will, to unique things. For those of us from the Lisp community, it's an interning operation. It basically just finds all the references, definitions, maps them up, and makes them the same. The execution engine, which happens at runtime, does the same thing when you class load. Actually, it's sort of partly class load, partly execute, but it's responsible for doing that same mechanism. And the way our binding model works today is that the compiler has to pick an exact signature and persist that signature, and we will bind to no other signature. So that means, for example, if the compiler said, I want a method on class A, and at runtime you don't find it on class A, but you find it on class A's parent, that's tough. We won't go there. Compiler decided exactly where to find that item, and we don't override that. That isn't the same as saying we don't do the usual thing of promoting types. That's actually the compiler does that promotion for us. We don't do it automatically. But the binding is against a specific CNAT compile time version.
Doesn't that make the riddle-based console come back? You move them and stuff across.
It does indeed. It indeed does. It does not. This does not give you the most robust late binding semantics you might like. And you'll see that that's actually I axed it, but it is one of the things we will revisit as we go on to version 2. But we're not going to do that now. It's sufficient for all the languages that we currently have, as it turns out. Well, in fact, there I said it. The next line. We're talking about an extension mechanism for some other. In version 1 for language-specific binding requirements. So, for example, VC has this notion of volatile that may not be shared by other languages, but you want some way of capturing that and getting the binding characteristics that belong to a certain language. That we have a mechanism in mind that we might be able to do. So it's an extensibility mechanism, but it still relies on compiler chooses correct signature. For V2, we're talking about language-specific fix-ups that could happen later, and that would be a way of resolving all the late binding issues. How do you get at the metadata? This is the answer to your question.
My question was more like, can you enumerate all the modules in a particular assembly, and not at a class level, but at a higher level?
Next week. It's an assembly question. It's next week. The answer is going to be yes, whether the current implementation does it or not. I don't think we've got a current full implementation of assembly, so currently the answer is no. But the answer will be yes. So the way you typically access this metadata is you can read the metadata, you can write the metadata. You can open the metadata for updating, so you could take an existing one and in what's called edit and continue mode, you could add things to it. You can enumerate through it, so you can say, I've just loaded a module. You can go to the module and ask, basically as part of the metadata operation, say, tell me all of your classes. For each class, you can say, tell me all of your methods, all of your fields, all of your interfaces, blah, 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 blah. Okay. And you can merge metadata from multiple sources. That's what happens in the link phase. There are two distinct ways of getting at the metadata. The current, the one that's in more use today is these unmanaged APIs that are sort of like COM-style calls that are enumerators and readers and writers. We are moving over to a managed version of that, which is called Microsoft.runtime.reflection, and that has all the same things that the standard one does. Plus, it also has a nice way of creating methods and providing the intermediate language directly and then persisting it out to a file. So you can actually, at runtime, create new classes, create new methods on them, create the bodies for those methods, and then instantiate instances of those classes and call the methods that you just defined. And then you can write that out to a file and execute it later also. It's actually very nice. Scripting guys like that. Yeah.
Does the class definition carry any version information or does it?
Yes. The class does carry version information in the, well, let me rephrase that. The module has version information, but presumably applies to all the classes within it. I don't believe the classes themselves have. Any of the metadata people here? I don't think. I think I'm right about that. I could be wrong. But I believe it's on a module basis now. So just some other topics. I don't want to go into any detail on this stuff, but we do have the ability of module-level functions and statics. That's your classic global functions, global static variables. So those are also supported in the metadata. You can also have references in this module to something that's in that module. So it's sort of it's exactly the traditional import table, export table for module-level information. We have a declarative security mechanism that, again, that would be, if we want to do it, that would be sort of the third in this series, is talk about the security model, but there's a declarative form of security, and the declarations are persisted in the metadata. And then we have what we call platform invocation services, which are the way from the intermediate language to call out to pre-existing, already compiled APIs. And when you wish to do that in the metadata, you put the information about the method as seen by is seen from the intermediate language, is seen from the calling side, I guess, plus information about the native calling convention needed to get there, plus information about what DLL it's found in, plus its mangled name, because we have mangled names in the world, and marshalling information for converting strings and converting other structures between the types as they're seen in the COM+ world and the way they're seen in the native world. Yeah?
So presumably there's some dual for that, for being able to let some pre-existing thing do a callback on?
There will be. That's actually scheduled for our next milestone. We haven't started to work on it, but we have. It's actually sort of weird. Right now we have the ability from COM+ you can call out, and once you're out you can call back. That all works. What we don't have is you started out outside and you want to call in. It turns out to be just enough different that it isn't the same. And that's scheduled for our next milestone. But I should also add that we do have it completely bidirectionally. If you're coming from COM, there's no problem. We manufacture COM interfaces. We consume COM interfaces. All that does work today. But if you're just coming from some random piece of C code that wants to call the function named f, that we don't do. Other questions? I think that's sort of, that was the end of what I wanted to say about the metadata. So the intermediate language, we have 3 documents you can take a look at here. basically, what's the intermediate language? Well, it's built primarily for the, but for the research audience, I should have changed this slide, but it has become part of the COM+ vernacular that is for type safety. More technically, it's for memory safety. It's for basically making sure you don't reference outside of your allocated memory space. That's the real primary design target here. It's intended to be source language independent. You really have worked quite hard to make it straightforward for languages, from a fairly wide spectrum of languages, to generate IL in a reasonable manner.
What languages, how wide is spectrum?
Well, to be honest, the real core, careful analysis has always been confined to the great three, all of which start with V. VB, VC, VJ, the late lamented VJ. In addition, we have specifically looked at, but not in anywhere near the same amount of detail, Haskell, Scheme, and ML. And we talk about, but frankly haven't done the real work on, Fortran and COBOL.
Script.
I'm sorry, absolutely, I'm quite sorry. We've done a lot of work on script, on several script languages that we handle. Yes, absolutely. Sorry about that. Herman will never forgive me. Yeah, so that's the range we're trying to accommodate.
So basically imperative and functional.
Imperative and functional, yes. We've not looked at, for example, the logic programming languages. We are trying to be architecture independent, in particular 32 and 64-bit agnostic, also somewhat endian independent, but that's really more problematic. Yes?
You build then for type safety, then you run code. Then what happens if you run code in C, which is simply not a memory-safe language? You can track memory.
Well, this is intended to make it, if you are in a memory-safe language, it should be easy and direct to generate this IL. It also has instructions which you can do whatever you darn well please with, and a verifier that guarantees that you can't do that. And you can turn the verifier off. Untrusted code. It's part of the security stuff, which is not scheduled for one of these talks, but is a whole topic unto itself. Another important goal was that the RAD tools can target this intermediate language, which has some funny constraints because you actually want it to be easy to generate and still maintain type safety and so on and so forth. So that's an ease of generation issue. We also want to hit the other end of the spectrum, optimizing target compilers. And we want optimizing compilers to target the IL in two different ways. It turns out you can, in fact, this is pretty much a standard compiler intermediate language, so you can do all of your normal optimization tricks on it and just emit it out. So I can give you lousy IL in and get good IL out. But we went a step further. We put in some, what they're called annotations, and I'll get back to this, which are things ignored by most of our jitters, but which provide, effectively as comments, information about analysis that has already been done to direct things like a register allocated to do a better job if it understands those comments. And so we want to be able to persist both optimizations and analysis that was done on the way towards optimization. Particularly important, at the very least, for the WinCE side of the spectrum, and it turns out at the extreme other end, at the McKinley end of the spectrum, because you want to do very good targeting of those architectures because your decisions will be very different on them. And there's sort of a whole broad range in the middle where you can get away without doing anywhere near as much optimizing. It is a stack-based model, and the goal was to make it easy to generate verifiable code, not just arbitrary RAD code. So stack machine, if you write in IL, then we are able, through fairly simple program analysis that's embedded in all of our JIT compilers, to produce lifetime tables that are used for the garbage collector, so that you don't have to, as a generator of IL, tell us anything about lifetimes. We can deduce it all from the information you gave us. That actually makes the work a lot easier for RAD compilers. You do have to give us exception tables. You have to know where your exception handlers are, where your protected regions are, where your filters are, where your finally blocks are. we assume a model that says all of the arguments, all of the locals are strongly typed, and that at every point in the code it is possible to deduce what the type of every element on the stack is. And it's not allowed to vary over different control flows through the program. And in order to make that deduction possible in an efficient manner for single-pass back-end compilers, we do make some restrictions on control flow. So you can't flow in and out of exception handlers. Yeah?
What's the local?
A local variable within a method, so you just declare a...
Wouldn't that be on the stack?
It's on the conceptual stack, yeah. But we considered it. But by stack there, what I meant by stack there is the intermediate value stack that's used for passing values back and forth between operations. So push A, push B, add. That's what I'm calling the stack.
So this is essentially the same model as the JVM then?
Could well be. For legal reasons, I have actually never read the JVM specifications. Actually, we think it will. Yeah.
So I'm
Surprise.
trying to wrap my head around how C and C++ are going to map onto this. What happens with C and C++ that has no types and so forth? Can't I in C and C++ violate the type system and do all these other nasty things? And I'm confused about how that maps onto this world.
Well, yes, you can on the values, but no, you can't on the locations in memory. C, when you say you get a local variable, you give it a type, you can't violate that type. You could put garbage there, that's correct, but the type is known. If you put garbage there, things will fall apart. Right? They'll fall apart for us, just like you do
You
for C.
didn't mention union types.
Correct.
Right.
Union types, it sort of depends on what you want here, right? If you're trying to generate type-safe code, you're not going to do that from the full C language. There's just nobody's even discussing or debating that. So the question is, all right, and therefore you won't be running our verifier. And therefore we aren't going to promise that your memory is not corrupted.
Okay.
Right?
Okay.
You will, however, not be allowed to have stated that that variable is of one type and use it for any other type, except for these weirdo operations.
And casts, right?
Right. Yep.
Is there a mode where you can turn that on even for C++, so you can guarantee that C++ is type safe?
It depends on what the it is that you meant to turn on. You can turn the verifier on, and what will happen is unsafe code that is generated will be rejected and won't run.
At runtime?
At runtime.
Is there a compile time check?
There is work in the VC and tools division to do languages that have that property, and I don't want to go there. It's a politically sensitive topic. The giggles around here are those people who know what the hell I'm talking about. So it's a different division of the company, I'm pleased to say. Fist I have not heard to the contrary. Right? So to just give you an idea of what the instruction set looks like, it's on the order of 200 instructions. It's growing a little bit. I'd say we're going to ship with on the order of 250 instructions. A bunch of arithmetic, including all the load constant instructions, a bunch of conversions between numeric types, the annotations I talked about, these sort of comments that are used for the optimizer, a bunch of stack access things for arguments and local variables, lots of flow control instructions, a bunch of stuff dealing specifically with the object model. You notice that's actually quite a very small set that deals with specifically the object model. And then a bunch of stuff for just copying data around. I only want to cover a few things because I actually did the overview of this in my last talk. So this is sort of drill down on a few things I did not get to then. One, which I've talked to several of the people in the room about, is our floating point model. And as several people know, we're actually inviting an external expert in next week to review this particular stuff on the next page. The current model is that we have a notion of fixed size real floating point numbers, and we support 4-byte, 8-byte, and whatever the natural size of your target platform is, numbers, and also as parameters. So for places where users put things, they have to know the size. On the stack, this is the evaluation stack thing, which users don't actively control. We have the notion of a floating point number that's as big as it needs to be, and it doesn't lose precision. It may get bigger if you do operations on it, and from a programming point of view, you don't actually know how big it is. So it expands based on what the target architecture is to encompass whatever's convenient on that machine. So if you're familiar with architectures, you'll know that on some, going from 4 to 8 byte is a really expensive thing. You're burning a lot of CPU cycles. You may, in fact, lose any hardware support if you go. So on those machines, things tend to stay in 4 byte quantities. On other hardware architectures, actually everything's being done in 80 byte units anyhow, so you might as well just go up. I meant 80 bit. Storing out of the stack into memory truncates. And if you're worried about that, there are conversion instructions that will detect overflows and stuff. In general, the model we use is the IEEE mode in which you never get an exception. You just get a special thing called a not a number. And then there's a special way to check whether what you happen to have in your hands is a not a number and turn that into an exception. That part, the first order, everybody's reasonably happy with, although there are details around the edges. These are proposed extensions that we're going to be talking about next week. One is to take all of our conversion instructions and add a prefix to them so that you can get conversion to integer in any of the IEEE modes instead of just having one defined mode. And that's as contrasted with global mode bits or modes, bits on a method saying which way things should be done. This would be on a per conversion instruction basis. And then the JIT compilers have to turn that into whatever the hardware does. Katmai and 3D Now support, we're talking about doing via a class library and teaching the JIT about those specific methods so that it will inline at high performance on machines that have those instructions. And we'll leave it as a standard instruction set on those that don't. And then direct access to the actual representation of floating point number for those people who are in the real high performance. I know my architecture. I don't care. I'm never going to run this on any other machine. Those people exist. Some of them may be in this room. Yeah.
So, on the first slide, the IEEE modes, are you going to have some of those different rounding control bits, that kind of stuff?
The proposal is to have those bits only on the conversion integer, not on the floating point add, floating point subtract, where they could also be. But we have not heard, the reason I'm having an expert in is to see if he knows any, but I have polled a lot of people in this company and nobody has given me a reason why they really want them on add, subtract, multiply, divide. And they're really costly to put there no matter how you choose to do it. So most people say, well...
What I was wondering is, are you guys picking the one way? IEEE has a bunch of ways to
do things. No, right now, we picked the one way. We know that's wrong. The proposal is that, at least for converting from float to integer, you will get all of the IEEE modes if you wish, but we picked the default one. And we'll tell you what it is.
I'll want to talk to you more.
I'll be glad to. Yeah. This is why we know there are holes in this, and we're trying to find out from the broad audience as we can what we should be doing. So I'd love to. With respect to control flow, mostly conventional, conditional and unconditional branches, switch statement, method call. You can method call to a known method, i.e. you actually embed in the stream where the class and the method name you want to go to. Computed via an object, which is both virtual and interface calls, or a general computation where you compute something and say that's an address of a method. That's obviously not type safe, and that's not verifiable, but it's there. And then we've also got tail call, so that you can say, call this, but there's no intent to return, so you can release my stack frame now. And tail jump, so pass my current arguments on there and get rid of the frame. Just pass my arguments on over there. And then exceptions. So you can throw them, you can catch them, you can have filter clauses, you can have finally clauses, and there's a way to leave the protected region and go to something outside calling the finally blocks on the way. Pointers and references. So the main thing we have in the language are objects. They're opaque. You can't peek at the address of the object. It moves. The garbage collector is permitted to move objects. Pointers, as distinct from objects, pointer types, are not allowed to point to objects. And you don't have to report them to the garbage collector. The garbage collector doesn't care because they're not allowed to point to anything it cares about anyhow. So that's why pointers and objects differ. They can point to a local heap that you've allocated yourself through the operating system, or anything. They can point to variables on your own stack, just nothing that the garbage collector might move around. So value classes on your stack they could point to, for example. Biref parameters, which are sort of like pointers, right? Implementationally they are pointers. From a language point of view, they aren't. And locals have to be reported to the garbage collector if they're allowed to point into an object. So if I say that I want an integer by reference, and then you say, give me x dot I, where that's a class, and I is an integer field of that class, you're going to pass me a pointer to that field. You're going to pass that as a biref. If that's in a managed object that might move, you better tell the garbage collector about it. So that reporting to the garbage collector has a performance penalty. That's why we distinguish the two. And biref values are not allowed as statics or on the heap itself. That statement's a bit strong. You can do it as long as you register them with the garbage collector. Yeah.
So is the verifier verifying the GC invariance?
Yes. Yes. It is aware of these. It guarantees there's no conversion between pointers and birefs. Right.
So because it might point to an object, etc., the verifier is the normal thing where it may reject correct programs because it's not omniscient.
A, that's true, and B, there's just no way to win. You picked up the point when I presented this 2 or 3 weeks ago. I actually explained the precise mechanism that the garbage collector uses to do a better job or that the verifier uses to do a better job. And it's sufficiently confusing that I didn't explain it here. But it actually is there, it works, and it's not as pessimistic as you might think. Turns out there are only like 4 instructions that ever generate an object reference, a biref that is on the stack. The verifier knows about those and allows you to treat those as pointers freely. What do we do to support the object system itself? These are the only, I think there are exactly 11 of these that really understand the details of the object system. Box and unbox for converting between value classes and instances on the heap. Allocating and initializing objects and arrays. Type references, those are those things where you pass both an address and the type of that address. The cast operation, the instance of operation, critical regions, which are sort of intermingled with the boss because you can guess why. Array operations, so fetching, storing, and getting the address of an element of an array. Loading, storing.
Are these vectors or multidimensional?
The arrays that are embedded in the actual instruction set are vectors, one-dimensional, zero-based. The class libraries use those to provide the usual multi-dimensional abstractions.
Well, I guess I have one more question
Yeah.
about there are machines out there now that are either SIMD machines or vector machines, and it looks like Intel may actually be doing some of that. By making arrays sort of objects instead of sort of base data types, do you in fact sort of create this little hole where there are arrays on one side and arrays on the machine side, and you have to sort of pass them through objects, or is this cat-my instruction, extension class thing that you've got, will that allow you to compile straight to array machines?
The array machines I'm familiar with are vector machines. You mean real multi-dimensional arrays?
Let's say vector machines.
Yeah. So and I haven't thought about this carefully, just sort of top of my head thinking about this. The instructions that are built in here, no, they do not. You do not get sufficient power from our abstraction to do vector operations directly in the instruction set. The trick we're using for the Katmai, or thinking about using for the Katmai, probably would work. That is, you write a library whose interface looks exactly the way you want it to, and is carefully crafted so that if you're on a vector machine, you could inline that code in 1 or 2 instructions per class call. And then we actually put a hook in the JIT so that it actually emits those on those machines, and when it's not on those machines, it just makes the function call that the user wrote in the first place. And then you use overloading and tricks like that at the front end so the users don't see you've got method calls and it comes out the back. The operations we have are load single elements, store single elements, so they wouldn't help. Typeless, we do have typeless add, subtract, multiply, and divide, so if you extended the type system, you might get away with it, but that turns out to be trickier to do.
Does this really come down to whether I can have like an array of 4 byte floats, and if the representation would be identical to the Katmai hardware representation?
And an operation to do something. The add instruction won't work. Our virtual machine instruction add does not accept a value class as an argument.
Sure. So you go out of the language to do that.
That's right.
But the important thing is that you don't have to relay out the memory.
That's right. That's exactly right. Yeah.
Jim, what about exception instructions? For any exception?
I couldn't call those control flows.
Okay.
So it's your choice. There is a throw instruction. It does take an object. Actually, at the IO level, it'll take an anything you care throw. It doesn't work for the rest of the world if you do that, but opt-IO is the way of persisting both analysis and optimizations from the front-end compiler like VC to our JIT compilers in the back end. And so it consists of all the normal IL plus some annotations that everybody else can consider comments. They do not affect the code. If you do not understand them, you can completely ignore them. They're really, from somebody's point of view, they're just inline comments. The model that we currently have, and there was a good deal of debate about this, but this is working so far, and we are getting ready to start doing the performance measurements to see if we have to tweak this. The front-end compiler, VC in this case, is responsible for doing register allocation for a machine that just by coincidence, I'm sure, happens to kind of look like an x86. And then there's actually a good reason for that. That's sort of the hardest case. And then everybody else has got a lot more registers. The question is, what could you do with the extra registers if you have them? And the way we handle that is you actually persist the interference graph for your locals, which is the hard part of the register allocation problem in the first place, is computing that graph. So you persist the graph, and then the jitter, who's on the target hardware anyway, knows how many spare registers he has, provides, that graph is ordered, and it simply walks through it in order and allocates as many registers as it can using those rules. That is never, it's A, never perfect, and B, it's not as good as if you actually ran that same register optimization that you had done on the C compiler with the correct number of registers, but it ought to get us pretty close. The other restriction is if you are writing opt-IL, and you actually do mark in your method, this is opt-IL, and only if it's marked that way will our opt jitter take it. You have to generate very simple trees. So you never have complicated nested expressions on the stack. There's both a depth limit and a total number of instructions limit. That, in theory, will allow us someday to write a finite state compiler that just has state for every possible thing on the stack, because the stack's limited. Currently, we do not have a finite state machine for this.
For your second bullet, since it hasn't left around a verification that this was the right register allocation, isn't it just as difficult to verify this?
Yes, we don't do it. In fact, while we state that you should be able to verify the annotations, and we believe that, we don't verify them. And so if you take this code, it will pass the verifier, and the opt-JIT may fail. The opt-JIT code may fail if the annotations were wrong. I'm sorry?
So it may fail.
It may arbitrarily fail, that's correct.
But then we use the regular.
Yeah, I mean, if you're worried about that, you could use the regular JIT, right? You know, it's a trade-off. It is a good point. There's a hole here. Yes.
So
Yeah.
maybe to say opt-IL safety events are off.
No.
I mean, well, that's what you just said.
No, it sort of depends on what you mean. Your safety bet is the compiler that's generated is safe. We don't independently check its safety.
That means safety. I mean, you're linking a whole bunch of random code in, and then you link it to code that does whatever it wants and destroy the system. Safety bets are off.
No, you could, for example, sign the code, run the very expensive verifier offline and sign the code, and not accept the code unless it's been signed as having been run through the expensive verifier that does verify the annotations. We don't plan to produce such a thing.
That's just going back to the trust model.
That's right. That's the trust clause. That's what he's asking about. Right? That's what is your trust model?
Trust is different from safety.
Yeah.
The question is,
Well, that's correct. It's also different from security.
in a chasing environment, this can be very, very dangerous. Because somebody can sign it and be wrong.
But I don't accept anything that's signed. I accept it's signed by those people that I agree should be able to sign, and I will trust that because they signed it, it did the right thing. And that's the trust model.
But if the user or whoever was afraid of crashing turned off the op jitter, they wouldn't have...
Yeah, there are lots of options here. I mean, if you're on a handheld device that is nothing but an op-chip, then you better be sure that what you're loading down is safe. Now, how you do that is something that, in fact, I mean, I just have to admit it, we haven't addressed it directly. We're not providing a tool that will check that those annotations are correct. We're only providing one tool that makes the annotations, and we believe it's correct, but other people might decide otherwise. And indeed, you've got a hole in that case. You wouldn't want to run the verifier needed to check this on a handheld device. It's going to run way too slow. It's got to redo the entire analysis and regenerate all of its tables. As you said, now I could provide you a tool that you run on the desktop to do that before you put it on the device. Or I could set up somebody who does that as a service. You send it to them, they run the analysis, they sign it, and then on my device, say if it's been signed by those people and those people only, then I'll accept it. All of those models are legitimate models. But just grabbing it down and running it, yes, that's a problem. Mm-hmm. Now you could, well, that's, yeah, enough said about that.
I don't mean to stop here.
Okay. Okay, so I think the only point I didn't comment here is the static single assignment graph, which can also be generated by an optimizing compiler, and is particularly good for doing loop optimizations, loop unrolling on the higher end machines. That can also be persisted. We do not currently, we don't generate compilers, but the VC compiler is not yet emitting that graph, although they are doing work to do that. And we do not have any of our jitters consuming that and using the information, but it's there, and we actually expect that will be important in the future. We also don't have handheld McKinley devices yet. So this, you can't possibly read this. Maybe I wanted to put this up because Tony pointed out a few bugs in my last version, and I actually got this to work, Tony. It really does work this time around. I couldn't believe somebody was just sitting there in the audience looking and said, "Hey, you got a bug there." Right? But I hadn't met him before, so that's what factorial looks like in IL. In our assembly, you declare that you've got a class, you've got a static method called factorial, it returns an int32. This is actually the way that you tell the assembler, please emit this metadata. This is a way of saying, emit a definition into the metadata that says I am defining a class with a static method of this signature. That's exactly what that is. This happens to be information that's required. It's automatically emitted by the compilers, but the assembler, you have to do it yourself, saying how much evaluation stack you want. Load my 0th argument, which is n, branch to, well, branch if that's false, which is the same as if it's equal to 0, down to the base case. Yes. That was the bug from the previous time. That's why you load it again. Thank you, Tony. Load the constant once. I mean, you know what factorial is like, right? This one wasn't there at all, but I'm proud that I got it to work, so I got to show it to you. This is the driver for it that actually goes out and prints stuff out. So again, this .global is just a way of saying emit into the metadata that there's a method not in a class, but rather in the module. It returns void. It takes an array of a class named Microsoft.runtime.string. It is the entry point so that when you compile this thing, you get an executable file that will actually start execution at this point. Load a static field on this class, which has, of this type from that name. Load your 0th argument. Grab the index into the array to get the number that's there. Call toInteger on it. Call factorial, and then call the virtual function that will write out a line given an integer. And I didn't actually show the output, but trust me, you type fact space 5 and it comes back and prints whatever factorial 5 is. I don't remember offhand. I tried it for 5 and 10, and I checked it. It really did work. For traditional reasons, we're calling this JIT compilation really a more technically accurate name these days would be client-side compilation. You'll see why in a minute. Our current system, and we've been criticized for this, but we actually think it's the right decision still. Yeah?
Probably more accurately client-side code generation. We're not compiling all that much.
I don't know. Yeah, maybe. I don't know what the difference between a code generator and a compiler is these days. Fooey.
The VC team writes compilers, I write code generators.
Oh, I see. Okay, fine. Well, in that case, since you've written one of these, it's clearly a code generator. Okay, fine. I don't care. Never mind. I'll take it offline. Our current plan is to have 4 choices for your client-side code generator. So one is our standard existing JIT. Now that is an optimizing compiler that is balanced for speed and performance, and it runs in reasonable time, and it generates good quality code, and it is the kind of thing you can do on the fly, and it's nice. EconoJIT is our replacement for the interpreter. It really is basically a threaded code interpreter. It just spits out native code out the back. It runs quite fast. So it digests arbitrary IL, emits native code out the back. Not particularly good quality code, but it still runs much faster than the interpreter would have if you average the time overall. OptJIT, which is the one that we've been talking about for, particularly this is what we'll be shipping for WinCE. That's what this gentleman in the back has been working on. That requires the use of the opt-IL. It doesn't take plain IL. It has to be run through the optimizing compiler. It has to have the annotations. It has to have the small trees. It runs in a small footprint, we hope. Actually, it is pretty small. It runs reasonably fast. It generates pretty good quality code. And so it's a good match for the handheld devices. And then sort of at the extreme opposite end of the world is what we started out as a joke, but I think the name stuck. We call UTC-JIT. UTC is the back end of the VC compiler, and it's arguably the best optimizing engine available in the commercial marketplace. And it ain't exactly what people would think of as a JIT. It doesn't have a small footprint, and it doesn't run fast. And you don't put this on your handheld device. You don't even run this on a per method basis. But our JITs don't have to run on a per method basis. It's just a bit of tradition. So the theory is you would run this at, say, install time. It sits there, it crunches away for quite a while. For those of you who were at the talk earlier this week, there was a talk in this very room about super optimizing high-performance computation. So you run that guy's code to actually match to this particular processor at this particular temperature, running in this particular latitude, right? And out comes the world's fastest, best code only 4 hours later. And then you turn it on, and it runs for the next year. And that's actually true. I mean, there are people who do calculations of that nature, and this would be a good match to those things. We do plan to publish the interface between the execution engine and the JIT. People might choose to write their own JITs. Turns out if you actually study our architecture, the intermediate language isn't built into the execution engine. The virtual object system is, but not the IL. So you could have your own, complete own language and plug it in here and still interoperate with other languages that use our IL. So I'm not sure I'll see many of those in the future, but it's a neat idea. I told you about OptIM already. So what happens? There's sort of two interfaces that are interesting. The EE to JIT interface, which is used at compile time when the JIT runs. So it talks to the EE and says things like, I've got this method reference token. Would you please tell me how do I find that? And back comes either a number saying it's at offset 27 in the object you've got on the stack, or here's a method you will have to call when the code runs to do that access, whatever. So that there's that kind of communication that goes across. The execution engine is responsible for stub generation and picking runtime helpers. So any time that the JIT's got sort of a hard job to do, typically because it's got some kind of method call or interface call or whatever, the execution engine gets called and it grovels around and creates the kind of stub necessary to do that. And in fact, it's the execution engine's job to do sort of the first phase of resolving interfaces, and it builds some code that has caching built into it and stuff to improve the performance at runtime of interface calls. The JIT itself actually produces two things. It took me the longest time to understand this. It actually produces two things. It produces the code for what you expect to run. It also provides a bunch of data that it hands back to the execution engine and says, this is the stuff you will need when you run to understand the code I just produced. And that has things like the garbage collection tables about lifetime, exception handling tables, which you actually produce some information about exceptions. The JIT actually, and the EE in cooperation with the JIT, produce a more elaborate thing that's more efficient in coding for runtime use that you wouldn't want to use in file formats because it's too big. And also the debugging information. So when you JIT code, you get back a mapping from original addresses to new addresses. So addresses as seen by the compiler in the IL to addresses seen in the native code. It's also, at this time, if you're trying to call a method that the JIT realizes, for example, is a native COM method or is a native API method, the EE recognizes that when you go and you say, I want to call that thing, and it produces all the marshalling information, and it optimizes the marshalling information at JIT time, so that what you get out of the jitter is in fact highly optimized for what was seen after compilation time. And that is responsible for a good deal of performance improvement in going across these boundaries compared to traditional virtual machines. And in fact, these stubs often turn into single instructions. They don't even become stubs anymore. They're inlined. What hangs around at runtime? These runtime helpers, things that the EE picked and said you're going to have to call these when the code runs. So they're things like the actual interface dispatch that has the code cache that says what I've seen lately. Arithmetic helpers. So for all the complicated pieces of arithmetic, the EE basically comes back and says that was too complicated for you to inline. So here's a thing that will do it in a slower manner. Object allocation. This is how we get, I don't have the perf numbers here, but we'll be talking about garbage collection next week. The allocation times are amazingly short. 6 instructions on an x86, I think, with 2 memory references for an arbitrary object. That all comes because at EE, at the time the code is compiled, you know enough about what you're going for, and you know enough about your platform to optimize the allocation and inline it in almost all cases. There's also what's called the code manager, which is sort of the other end of it. These are things that you've compiled, you the jitter compiled code to call these. The EE periodically wakes up and calls these guys. For example, I want a garbage collector. An exception just occurred. I need to walk the stack. And remember I said the jitter produced code and management tables. These use those management tables in cooperation with pieces of code to walk back one frame on the stack so you can walk the entire stack at runtime. find some security data. I told you there's this declarative security story that we might talk about another time. That information is embedded on the stack in places that you can't get at from type-safe code. So there's a way to get at it this way. You can also get to this pointer, so if you want to know what method you're in. It also decides when it's safe to do garbage collection. So you actually can stall off garbage collection for short periods of time, and that's handled through this mechanism. It's also how you report your references to the garbage collector. It's how you invoke exceptions and filters and so forth. The whole idea of this mechanism is to sort of partition the problem so that the JIT makes the decision about what are the GC safe points, how it wishes to encode the reference, the GC object references. It can make any decision it wishes when it compiles the code, and it hands off whatever tables it chooses to the execution engine to hold. And then when they're needed, it goes back to the execution engine through this mechanism and says, would you please give me that table I gave you earlier? I'll poke around with it and give you the answers you just asked for. So it's sort of a handshake across there. So that's actually all I wanted to talk about today, which is good because I ran over by 8 minutes. I would like to do two more things. One is ask for questions. One is talk about whether, we'll obviously do the one next week. I'd like, for those of you who are going to come back, think about other topics you might like and whether or not this has been a useful hour and a half. I don't want to waste anybody's time. On the other hand, if you think these are useful and we ought to plan more, I'd like to know that by the end of next week's talk. So these are some of the topics that I thought might be interesting to have discussions about, but I'm really completely open. Questions? I find it scary when nobody except you all.
Well, the x86 just counting instructions makes no sense. I think the next time you have a slide showing the 6 instruction sequence, because then we know what's really involved.
Oh, next week's talk, I'll tell you right now, next week's talk, we've got 1 hour again, plus questions. And I'm giving 15 minutes to each of the 4 groups. And the garbage collector, Patrick, will be either doing the presentation or giving me the size to do the presentation. And you'll get 15 minutes at whatever depth we can get into 15 minutes. So that's one of the topics. I hope that gets in. But Patrick will have to decide. So there's that level. There's also the what do we do on multiple heaps and what's the actual algorithm used. And you can't cover all that in 15 minutes. So, questions, comments?
About threading and
some of that's going to be covered next week too. That is not really, the threading story in particular is not finished. The SMP story sort of depends on which piece of it you mean. The garbage collection and stuff like that we understand really pretty well now, but there's lots more to the story than that we don't. The remoting story is coming into focus, and we'll give you what we've got on that next week.
Just, if you do a third week, I'd just like to vote for more discussion on security.
Yeah, okay. What?
And performance.
And performance. Right. Thank you.